So I'm a physicist by training, and also I got contaminated by becoming an executive. I had some interesting experiences, including working with PER. I'll describe those toward the end of this. But I wanted to talk a little bit. I heard just now Internet of Things. Maybe that's not a big deal, or maybe it is. I'm not sure I really understand Internet of Things. I think physically about things. The application I have is sort of like distributed Internet of Things, but you're actually doing some things with physics to get some information, and then using computing to go and analyze what it is. So let me tell you a little bit about this. I'll go quickly. Spectral ID is a new thing. It's basically a way to identify something. I'll show you how it works and how to obtain spectra, and then how to use it with the cloud to figure out what things are. And what kind of things will that be? I'll tell you a little bit about that too. Computing requirements for these, that's a token slide that's in here because I'm at a computing conference and I'm a physicist, so I have to put something in about computing requirements. But the fact is, this is going to look pretty familiar to you once I describe what we're doing. So if I ask you to identify something, you say, what is it? I hand you a stone or something. You know, you're going to look and say, well, do I recognize it? These are some of the questions you ask. How much does it weigh? What's it feel like? What color is it? If you're an American, you're going to ask, can I eat it? That's something that we, very big in America, If another question is it stupid? But we're not going to go there. Oh my God, I'm on film. Look at my passport. But the actual way to identify something is to recognize that every material on the planet has a distinct energy spectrum. It's a quantum mechanical statement about what it's comprised of. And because of that, you can shine light onto it and look at what comes off. Physics is typically a field where people describe it in very complicated ways. It's a field where you take stuff, smash it together, and see what comes out. That's what you do. It's what you do with a Large Hadron Collider. You do it here in optics too. So we shine light on a material, we look at what comes out, we get a series of curves showing the frequency or the amplitude of light at different wavelengths or frequencies. As you change the composition of a material, that curve will change. So that means there's an identity to be associated with the kind of curve you get. Okay? Here's a better example. A series of uranium phosphate materials. Don't worry about what they are. I'm not sure I know. But if you take their spectra and you plot them, you can see that if you look as a distribution of wavelength, the amplitudes are very different. They have different shapes. So that means that if you can capture the shape of something in its spectrum, you should be able to ID it, right? And so that's what we do, is we take a sample, we get its spectrum. It's like a fingerprint of a material or a thing. Could be a bacteria, could be an insect in the field, could be a piece of a leaf that's on a vine. So you want to figure something out about the state of health of your wine. You go ahead and you capture that spectrum, and then you look at the fingerprint. Normally what happens here is that when you're a student, you say, well, I got a spectrum. I'm going to go upstairs and ask the guy who knows everything. I pointed to you. In physics, there's a lot of equivalence, believe me. And I need to go to them and say, what is this? And they go, well, my experience says that's probably an emerald stone, but I'm not really sure. What we do then is say, well, heck with that. We're going to capture a library of images such as these, where you take a spectrum of an organic object or an inorganic object. You get a curve, you colorize it, so now you have an image which has a shape, distinct peaks, and colors, which you can now run against other images. You need an instrument to do that. Typically, that guy you go talk to upstairs in the lab is really smart, really crotchety, that's cranky. We'll have a big machine like this and tell you to stay away from it because you're a grad student. You're going to ruin it, and that's pretty much what I used to do. But, we designed something that's a lot smaller and compact and battery operated. You can carry it around with you. And so you have now an object which can take a spectrum anywhere. If you take the spectrum, you combine it with metadata. Our idea is then that when you turn this thing on, it will communicate through the internet. It may have to get there through a telephony network or Wi-Fi. It'll be identified at the other end. It'll say, okay, I know who you are. You're somebody from a vineyard. You've been here before. You have a library of images. You're giving me a new one. Here's some of the library images that you have. I'm going to spit back an answer and tell you what that is, all in about maybe after you take the spectrum, maybe 50 microseconds. It's not going to be a lot different than a Google search. It actually works like this. If you use commercial software, you can actually do the image analysis this way. And so we propose to do this and have actually put together a system where we have different objects. We're collecting the data. It's going to be collected in user models. So somebody who works in wineries or works in the fields or works on farms will have a set of images. And they'll be able to access those directly. There's also content libraries where you'll be able to look at those and compare and find out what your image is. And it's important to do that because if you actually have a set of sensors, Internet of Things, that are all collecting spectra and distributing it back to a central location, which may be located nearby or it may be at the other end of the cloud, you'll be able to look at the results in a field and say, do I have a disease in my plants? If I do, where is it? Is it all over the place? Is it propagating in my field? Does it look like it's a disease propagation like a small world network? Is it something that I can stop by cutting out part of my field? You can do that also with growth. You can do it with pollution on the beach. You can do it in a factory and quality. These things are actually Internet of Real Things, where you're collecting information that represents the physical state of the material and trying to identify it. So the computing needs for these are pretty trivial, actually. And so I didn't bring anything new here. It's a good thing to hear that architecture is dead because now I don't have to worry that I didn't bring anything new. Okay, but for the measurement side, we just need low power processors and big memory. If we can put a lot of images locally in one of our instruments, we can get a lot of information before we send it out for a big comparison. Low power displays and comm chips, that's pretty straightforward stuff. The local networking or the clustering of these things in the field, there's nothing unusual about that. The hardware and the software exist for that. We have our own software for mapping the results from different areas. And what you want to be able to do is actually have a display where when you get all the measurements in the field, you can look at the display and it'll tell you what you've seen. You have a disease here, it's propagating, or do you have a mature field here that's less mature here? Compare that then with a sun map or a watering map. You can figure out how to manage your crops. If it's crops you're worried about. If it's a factory, you're going to be worried about quality control, things like that. The internet's fine as it is for this. We've already used it with commercial search engines from Google and Facebook, and one from Clarify. So this is a technique that actually works to be able to capture information. It's a physics thing, and do image recognition and get a result as you stand there looking at your work. Now, this is a really important thing, and it leads into my discussion of the most important topic here, is PER. Okay, so PER is on the left here. I'm not sure if you were aware. That's me on the right. In the center is a design of a microprocessor called ROC from Sun Microsystems. Per and I met in about 2000, was it? Yeah. I was running a group, a physics group actually, an architecture group as well at Sun. And we were informed that we had problems with our computers. It turns out that the problems were due to the Big Bang. Who would have thought that, right? But it's true. It took us a long time to figure this out. But after a while, we discovered that cosmic rays from the Big Bang were smacking into the atmosphere, generating neutrons. They were getting to our caches, which were protected. So they would crash the machine, but they weren't backed up. There was no error correction. And this was a bad idea. That was an architecture thing. I learned all about this from him. I came to Sun to do optical interconnect technology. We were going to connect clusters with photons. That's what I wanted to do. And instead, I have to solve physics problems for computers, and I have no idea how a computer works, except that you turn it on and maybe it boots. And by the time I got out of Sun, I knew a little bit more than that, thanks to Per. And since then. The things that I learned, though, that were in the near term that really made a big difference to me were how to understand somebody like Mark Tremblay when he's talking about his ROC processor. How does it work? How do I design a system around it? I ran the group called Supernova. I named that group. that was the computer system for that chip. And Per was instrumental in both educating me and working with my team of people, and also bringing in talent. So Magnus Ekman came in, he was working with us, I hired him. Ashley Salisbury, who had worked with Per, he was also in my group. I put him off in a virtualization area because he had the strength to deal with the Solaris people who had a real attitude problem. The thing on the right is actually the most latest thing that Per and I were working on, which is 0-point technologies, which is memory compression. And that's another startup. The first startup that he and I worked on together was called NEMA Labs, and it was in, what, 2008, something like that?
Yes.
And it was a really great idea for automatically threading C and C++ code for multi-core. That's, again, another area where Per taught me something I didn't know. Looking at the bottom left, you know, I had to worry about the problems there of heat, because I'm a physicist, and our computers got hot. How do we get rid of the heat? But the architect said that's not the problem. The problem is that those two curves are not, they're not going together. Yeah, there's a new paradigm coming in. I think it was the Afara company or Afara project with Stanford and Kun Lee, which got Sun Microsystems into multi-core systems. And ultimately, people like Mark Tremblay were really smart, and also Eric Hagerson, who was there at the time. We ended up with a processor that we could build a system around. So without Per, I'm not sure where I would have gotten to. I mean, I would have gotten the physics right, but I didn't understand how a computer worked, and Per really taught me that. So I thank you very much, or I blame you. I'm not sure which one. And I'm just very glad you invited me here. Thanks for listening, and it's really good to know you and your family.
Thank you.
Thank you.
Thank you very much. Are there any questions for Rick?
You talked about crop diseases and water pollution and factories, and you didn't say anything about medical diagnosis, and I wondered why, because it seems like what you have outlined, the spectral analysis, et cetera, is a natural for a critical problem today and moving forward.
Right.
You know, human disease analysis. And
So it is, in fact, spectral analysis is used in medicine. And in fact, it's not going to be those small machines like I showed you, but these big monster machines. Because what you're looking at with spectra, you're looking at Raman spectroscopy in particular. I'm talking about photoluminescence here. But whatever you use, you're looking for cells that are living and moving. You need to pick up signatures of what's there. The best way to do that is to smash it up and look at its DNA. And that's pretty much what companies like Illumina provide big equipment for, sequencers. But if you're doing spectra, you can do a great deal with spectral analysis. It's just not distributed, it's located in one lab.
so the problem is that every random hospital can't afford these monster machines.
Right.
And what we want to be able to do moving forward is to be able to do this thing in the field that then you could ship to the place where it's needed.
Well, it's a great proposal you're making, and because I'm the guy running this company, it's something that I would really like to get us in. Yeah. The difficulty we run into with it is to actually do anything that involves humans. There's a huge barrier. Now, that's not a bad thing. I mean, you want to get over that barrier. If we could break into that and get hospitals to use these and doctors' offices, we'd be very wealthy. But also, humans would be much better off. That's the prime thing. I think there's a big leap to get there. But there are other instruments that people are working on to try to make more portable diagnostic equipment. So it's not a dead end by any means. It is a target for us. Yeah. Thanks.
Are there more questions for Rick? No? Then thank you very much, Rick.
Thank you.
This is a small present for you. Thanks a lot.